Hello, Assalamualaikum. My name is Azeq Naufal, and we are from Group 3, and we will be presenting about the topic resource access control. So, this is the table of content that we will going to cover. So, firstly, we're going to learn about assumption, and then resource definition, and then task state diagram, priority inversion protocol, which is divide by 2, which is priority inheritance and priority ceiling. And lastly, we're going to learn about example. So the introduction for resource access control. In a system where many tasks run at the same time, they often need to use the same resource, like memory, a printer, or a sensor. If two tasks try to use it at the same time, it can cause errors or system crashes. Resource access control is a way to prevent this by making sure only one task uses a shared resource at a time. This keeps the system safe and running smoothly. Common methods include using logs, semaphore, or setting rules based on the task priority. So right now I will cover about assumption. There are three assumptions, which is periodic tasks. Tasks can have resource access and also RMS scheduling. And for the periodic tasks, there are tasks that repeat regularly. For example, a task that runs every 5 seconds, and they are common in systems like sensor or alarms. And then for tasks can have resource access, tasks may need to use share thing like memory or a printer. If two tasks use the same thing at the same time, it can cause problems. So we use log to make sure only one task use it at a time. Okay, for the last assumption is RMS scheduling, and that we known as rate monotonic scheduling. It is a way to decide which task run first. Um, for this point, the task with the shorter period always get the higher priority. For example, task A run every 10 milliseconds and task B run every 20 milliseconds. So we take as task A the higher priority and task B the lower priority. It is a simple and work well if the tasks are planned properly. And now I will explain about the resources. So let's we take a look about resources may represent. Firstly, hardware devices such as sensors and actuators. These are memory capacity or buffer space. Software resources such as mutex logs, queues, and so on. And then let's we assume a system with type of resource. Each resource comprises indistinguishable unit. So the resource with an infinite number of units have no effect on scheduling. Each unit of resource is used in a non-preemptible and mutually exclusive manners. Resources are serially reusable. If a resource can be used by more than a job at a time, we model that resource as having many units, each used mutually exclusively. And lastly, the system must control access to the resource.
My name is Hidayati. I'm matric B082210459. Today I want to present. So let's start by understanding how tasks move through different states during execution. A task begins in the ready state, is prepared but waiting to be scheduled by the CPU. Once scheduled, it's moved to the run state where it actually executes. If the task needs a resource that currently unavailable, it enters the waiting state. Waiting state, when the resource becomes available, it goes back to ready, waiting for its next chance to run. This cycle continues until the task finally terminates after completion. Now, let's talk about a specific scheduling issue called priority inversion. Priority inversion happens when a higher priority task is blocked, not by another high priority task, but by a lower priority task. The cause is usually a shared resource. The lower priority task log it, and the high priority task end up waiting. What worse is that delay becomes longer if a ta- medium priority task run in between, causing unexpected performance issue. So here a visual example to help us understand it better. At the bottom, we see T3, the lowest priority task. It starts first and log a shared resource. It shows in red. Next, T1, the highest priority task. Try to run but get blocked because the resource is still held by T3. Then T2, a medium priority task, arrive. It does not need the shared resource, so it run and delay T3 from finishing. As a result, T1 is stuck waiting. This is the priority inversion, and it can last as long as T2 keeps running. Finally, once T3 finish and release the resource, T1 can continue.
Assalamualaikum. My name is Isyraf, so I'm going to continue my presentation for this topic, which is a priority and inheritance protocol. So, what is that? It is meant by a solution to the priority inversion problem where a low priority task temporarily inherits the priority of a higher priority task that it is blocking. So it is to ensure that lower priority tasks do not unnecessarily delay higher priority tasks by allowing them to temporarily inherit the higher priority. So how it works? Let's say we have three tasks, which is we have task one, the highest priority, the task two is the medium priority, and task three is the lowest priority. So how it works is the three tasks logs a resource S, which is could be real text, and they say it's real text. Task one becomes ready and tries to access S but gets blocked because task three holds it. And then task two medium priority becomes ready and would normally preempt task three. Under priority inheritance, task two temporarily inherits task one's priority to finish its task and release S, which is the mutex. And then once S is released, task 3 reverts to its original priority and task 1 resumes. So characteristic. I will use characteristic based on the previous example. So the first one is temporary priority boost. Low priority task runs with higher priority until resource is released. Transitive inheritance. If multiple levels of blocking occur, task 1 has priority, highest priority, and task 2 the second one, and this last one is task 3. Task 3 inherits task 1's priority through task 2. So for priority reversion, after critical section reaches the vertex 5, task returns to original priority, and the dialog could occur if multiple tasks hold and wait for resource silently. So let's jump to pros and cons of uh, priority inheritance protocol. So for the pros is number one is soft priority inversion, and then it could also simple to implement, and it can improve response time for critical tasks. And for the cons part is can lead to deadlock in poorly designed system. Priority boost may cause unexpected task preemptions and lastly more complex with transitive inheritance.
Assalamualaikum. My name is Muhamad Abrisam bin Jusoh. For part Priority Ceiling Protocol. What is Priority Ceiling Protocol? Priority Ceiling Protocol solve the priority inversion problem without getting into deadlock. For each semaphore, a priority ceiling is defined, whose value is the highest priority of all the tasks that may lock it. When a task Ti attempts to execute one of its critical sections, it will be suspended unless the priority is higher than the priority ceiling of all semaphores currently locked by tasks other than Ti. How the protocol works. If task Ti is unable to enter its critical section for this reason, the task that holds the loop on the semaphore with the highest priority ceiling is said to be blocking Ti and hence inherits the priority of Ti. As long as a task Ti is not attempting to enter one of its critical sections, it will be preempt every task that has a lower priority. Properties. This protocol is the same as the priority inheritance protocol, except that a task Ti can also be blocked from entering a critical section if any other task is currently holding a semaphore whose priority ceiling is greater than or equal to the priority of task Ti. Prevent mutual deadlock among tasks. A task can be blocked by lower priority tasks at most once. Priority ceiling protocol example. Three periodic tasks with different priorities. Task A, highest priority. Task B, medium priority. Task C, lowest priority. Shared critical section resources. CS1, CS1 and CS2. Priority ceiling assignment. Both CS1 and CS2 are assigned the priority ceiling of task B since it is the highest priority task that access them. Execution timeline. At time T0 to T2, a task A begins executing and lock CS2. At time T3, task B become ready and attempt to lock CS1. However, CS2 is still locked by task A, and its priority ceiling equal task B priority. According to the protocol, task B is blocked because it cannot lock a resource while another resource with the same ceiling is held by a different task. Priority ceiling protocol response. Since task B is blocked by task A temporarily inherits the priority of task B. This allows task A to continue running and finish its critical section faster. After task A complete and release CS2, task B is unblocked and proceed to lock and use CS1.
Now, let's take a real-world example of parity inversion from the NASA Mars Pathfinder mission that landed on July 4, 1997. The mission used a real-time operating system called VxWorks, which scheduled tasks based on priority. There were three main tasks in this mission, which is T1, the information bus task, had highest priority and was responsible for critical system function. T2 was communication task, which is medium priority, and handling data transmission. T3, the meteorological data collection task, was the lowest priority, collecting environmental data on the Mars. These tasks are accessed shared resource, which is the information bus, protected by a mutex to avoid conflicts. But here what went wrong. The low priority task T3 locked the mutex, and later the high priority T1 tried to access it, but got blocked. Because the mutex was still blocked, T1 could not proceed. In meantime, medium priority T2 keep running, which further delay the unlocking. This created a classic priority inversion problem. Eventually, the system failed to meet its timing requirement and was reset by the watchdog timer. So for the next slide, this diagram shows what actually happened in more detail. Let's walk through it from the bottom to top. The task at the bottom, ASIMET, is the low priority task. It starts execution and lock the mutex to use a shared resource. While this task is running, The high priority tasks BCDISD become active, shown at the top. It tries to access the same resource, but it blocked because the mutex is still held. Now, instead of letting ASIMAT finish and release the mutex, medium priority tasks in the middle are allowed to run. The preempt ASIMAT, which prevent it from finishing and unlocking the resources. This means the high priority tasks stay blocked for the longer than it should. The red arrow in the diagram show how interference by medium priority tasks worsen the problem. Eventually, the system detects an overrun, the task has missed its deadline, and trigger a system reset during the watchdog timer. This situation was fixed when the engineer activated the priority ceiling protocol, which prevents the medium priority task from the interfering when a lower priority task is blocking a higher priority one. After this, the system worked as expected.
And Assalamualaikum, my name is Hakim. For next slide is blocking time and scalability. Priority selling. When a task look a semaphore, its a priority is raised to match at the selling level after the semaphore. This help the system prevent deadlock and ensure the task in only blocker on. However, the task cannot be suspended while inside the critical section. And then for modeling blocking time and early deadline. If a task is blocked by a lower priority task, its CPU use increase. The increase equal increase we using the calculation increase equal to BI divide by PI. And then if a deadline is early then the priority, the difference include the extra blocking. So EI equal to PI minus DI. And then for total increase, we using BI plus EI divide PI. Okay, for next slide is we talk about the example. So we using task 1. The priority is 8. Execution time is 2. Deadline is 7. Blocking time is 3. So we use for extra use, we using the calculation. The formula is B1 plus E1 divide P1. So 3 plus 1 divide 8 equal to 0.5. For total utilization, we using the formula C1 divide P1 plus B1 plus E1 divide P1. So 2 divide 8 plus 4 divide 8 equal to 0.75. And then for scalability check, tasks are solved for highest to lowest priority. So T1, T2 and Tn. For check scalability, add the blocking time to the task execution time. So Ci plus Bi. When a calculation completion time, we using the Ci only. And then for higher priority task, we using Cj. Okay.
Good evening, my name is Sharvin and I will be continuing with RMS scheduling with shared resources. This is task segmentation using critical sections. So task T2 and T3 access the shared resource R, and each task's total time Ci is split into Cix, which is before, Ciy, which is a critical section, and Ciz, which is after. Real-time scheduling must consider these critical sections to avoid priority inversion. Okay, so next we have priority inversion in RMS scheduling. Blocking without and with priority inheritance. So without priority inheritance, T3 starts and locks resource R. T1 preempts T3 but gets blocked waiting for R. T2, which has a medium priority, preempts T3 and runs. T3 resumes and releases R after T2 finishes. T1 is blocked longer than necessary. This causes unpredictable delays, which causes priority inversion. So with priority inheritance, T1 blocks on R held by T3. T3 inherits T1's priority temporarily. T2 cannot preempt T3 anymore. T3 finishes its critical section and releases R. T1 resumes as soon as resource is free, and the delay is predictable and minimized. So next we'll be looking at stack-based priority sealing protocol. So based on original work to allow jobs to share a runtime stack, extended to control access to other resources. So sealing is when all resources are free. Right? Let's say pi t equals to omega. So pi t is updated each time a resource is allocated for free. Pi t is current priority sealing of all resources in current use. Omega is a non-existing lowest priority level. So in terms of scheduling, after a job is released, it is blocked from starting execution until its assigned priority is higher than pi t. Non-blocked jobs are scheduled in a preemptive priority manner. Tasks are never self-yielding. Allocation whenever a job requests a resource is it is allocated the resource. Allocation rule looks greedy, but the scheduling rule is not. So now let's look at an example. So job characteristics are J1 RI is 7, EI is 3 and locks into 1. J2 RI is 5, EI is 3, locks into 1. J3 RI is 4, EI is 2. There's no critical section here. J4 RI is 2, EI is 6, it locks 4, then 1.5. J5 RI 0, EI 6, it locks 1. So behavior protocol, jobs blocked from starting if priority is pi t. Jobs can only begin execution once safe to do so. Fewer context switches compared to basic protocol. Jobs don't block mid-execution, which is better for predictability. Deadlock is also avoided, and all jobs finish, but some start later for safety. So now we'll go on to characteristics and maximum blocking time. Characteristics: when a job starts to run, all the resources it will ever need are free. No job ever blocks waiting for resources once its execution has begun. When a job is preempted, all the resources the preempting job will require are free, ensuring it will run to completion, and deadlocks can never occur. Longest blocking time probably not worse than the basic priority sealing protocol. In example, not worse than the duration of one critical section. So now we go to blocking time. The priority sealing protocols implement avoidance blocking and so do not exhibit transient blocking. Block for at most the duration of one low priority critical section. Direct blocking low priority jobs locks resource can be blocked up to the duration of the critical section of that job. Avoidance blocking uh, is resources free, but priority sealing rules may deny access. So lastly, we come to resource access and communications in POSIX. So semaphores, mutexes, and message queues. So semaphores are a basic locking tool. Uh, Types are like counting and binary 0 or 1. It's used for mutual exclusion, so simple access control. Mutexes are advanced locking for real-time tasks. They can control task priorities during resource access, can use protocols like priority sealing for better scheduling. Then we go to message queues. They enable communication between tasks. They can send signals or messages without direct synchronization. For example, queue protected by a mutex and condition variable. Thank you.